Well, it's really nice to be here today. I think we had a real good introduction from our director on the importance of point source pollution control. I mean, it's a huge issue that we're dealing with. Point source control is necessary, non-point source control is necessary, ag controls are necessary. We're fortunate to have a regulatory program on the point source side that allowed us to accomplish a lot of these goals. So I think that's really important to know. But we also have really willing participants on the municipal side, like Majid helped us so much from Great Lakes Water Authority, and other municipalities are also helping us move forward. But it's also important for us to stress that we're using operational controls where possible. We got good agreement from EPA to continue to use that program instead of direct water quality based limits and their permits. So it's really important for us to progress in a reasonable way for point source controls and accomplish that through the regulatory program. So this is a success, and I know we're going to talk about a lot of other things today, but this is a success in our program, and Tom's going to do some of the details. All right. Everything we do in Water Resources Division is to protect designated uses. I think the director talked a little bit about that, but point sources are really important. Non-point sources are important to protect all our designated uses and protect our waters. In Michigan, water defines us, as you can tell. It's also the 50th anniversary, a couple years past, of the Clean Water Act. That's such an important document that established the regulatory program on the federal side. We're a delegated program since 1973. It's really important for us to implement the Federal Clean Water Act. It's a statute that has so much value in improving water quality across the nation. So I'm going to talk a little bit about impairments in the Western Basin. This is just going to be really brief, but the Western Basin is really shallow. Large algal blooms in the spring and summer result from point and non-point sources, total phosphorus. These blooms produce toxins, that's why they're called harmful algal blooms. And in 2014, we had a huge issue based on detecting of these materials in the intake at Toledo drinking water facility that caused a lot of issues. So there's real world impacts from the impairments that we see in the Western Basin of Lake Erie. We've done a lot in working with our communities and our regulated partners to help control total phosphorus in the Western Basin. One was the 2012 Water Quality Agreement, Great Lakes Water Quality Agreement, that set the targets for us to achieve. And then in 2015, before the Domestic Action Plan, we reached a collaborative agreement with Ohio and Ontario in order to establish some of these goals. One was the 20% reduction goal by 2020. That was an aspirational goal. The next was a 40% goal by 2025, and our directors mentioned that we're struggling to meet that. In 2018, we had our first domestic action plan, and it was followed just this year, and you have the QR codes for the new domestic action plan, the revised one. It's in 2025. So this is a complicated slide, but I think the important aspects are Michigan has to achieve a 40% reduction ultimately, and that's 725 metric ton reduction in order to meet that 40% reduction. Just so we know where point sources stand and non-point sources stand, with the two phases of the program that we have to control total phosphorus, that will achieve about 2/3 of the 725 metric ton reduction from point sources. And I think it's important to note that from point sources, we've been able to do significant reductions. So what we're asking for is another 1/3 of that to be accomplished through ag sources and non-point sources as well. So the big thing is we have the Detroit River as one of our priority watersheds, as well as the Raisin River and the Michigan portions on the Maumee River. The Detroit River itself is point source driven, and because of the large wastewater treatment plant there, Great Lakes Water Authority, plus some other large wastewater treatment plants as well. The Raisin River is dominated by ag sources and non-point sources. Same as the Maumee, the Michigan portion, that's also non-point sources and ag sources. But overall, we talked about the 2/3 reduction being from point sources, 1/3 from non-point sources. This is a really good graph. I think it shows where all our point sources were for our key wastewater treatment plants. That's phase one. There was 4 key wastewater treatment plants. One was Great Lakes Water Authority, and you can see that's the dominant source of total phosphorus to the lakes, but that's because it serves 77 communities. It's the largest single-site wastewater treatment plant in the United States. It has a maximum flow that can be discharged during wet weather events of 1,700 million gallons per day, so it's a significant source. We got the commitment early on back in 2012, 2013 with Great Lakes Water Authority and DWSD at the time to make some important operational changes at the wastewater treatment plant and accomplish this. So you can see over the years, there's been a significant reduction in point source flows from these key wastewater treatment plants, and they're the most significant. About a 400 metric ton reduction alone from Great Lakes Water Authority. This is a nice view of the wastewater treatment plant, Sug Island, where it's located on the Detroit River. And I always like this picture too. It's from the top of the incineration building, is that right? And looking back towards downtown across the secondary clarifiers as well. So what phase 2 is looking at these key wastewater treatment plants, and they've achieved basically a 0.6 milligram per liter growing season average from April through September of total phosphorus. So that's a reduction from what Michigan has done in the past, which was 1 milligram per liter. But now we've worked with EPA, and EPA has been a strong force in making us do more. So I hope EPA continues to do this effort for other states as well, that I think also have point sources that are significant. And I haven't seen yet some of the changes in other wastewater treatment plant permits as well. So something to look forward to. So we have the 4 key wastewater treatment plants, and then we have another 21 wastewater treatment plants for phase 2 that we're working with. I talked a little bit about the growing season average, the 0.5 milligrams per liter that we ultimately want to meet. That's consistent with the Great Lakes Water Quality Agreement. The 4 key plants are already meeting that. 9 facilities are already meeting tighter limitations because of local concerns. But those other 12 facilities we're working with on a watershed basis in order to achieve those limits. So we appreciate the efforts of additional wastewater treatment plants, and some of those folks are in the room today on what they're going to do over the next 5 to 10 years in order to achieve the 0.5 milligrams per liter growing season average consistent with the Water Quality Agreement. All right, I want to introduce Tom Asmus. He helped us so much on operational control through the state. And what is really important for us, and I said that in the beginning, is our point source controls. We didn't want to expect our plants, because there's so many other things that they're working on, from wet weather control, CSO control, SSO control, other things, tighter ammonia limits, for example. So they're working really hard. So what we wanted them to use were operational controls where possible, instead of large capital expenditures in order to meet limitations. So if Tom can come up and talk about that aspect, that would be great. Thank you.
Good morning, everybody. Thanks, Bill. I am going to just elaborate a little bit on the guidance document that EGLE had generated a couple of years ago that Phil Roos had earlier mentioned today. Before I forget, I put 2 copies of that on the table and back if anybody's interested in looking at it, or it's available off of EGLE's website. So this document, I'm used to reading tech manuals. I read engineering, design manuals, manuals of operation for municipal wastewater treatment plants. We refer to them as public and treatment works. This was a breath of fresh air. It's really well written. It's got a lot of graphics. Unlike many EGLE documents you may see out there, it's got good illustrations and very clear and concise descriptions of these processes. So the purpose, as Phil had just suggested, we're looking at internal measures. I'm going to just touch in 10 minutes. I can not tell jokes, and I cannot go too deep into the technology. So these are probably by design. But Phil had mentioned we're looking at operational internal adjustments to plants as an alternative to big capital intensive projects to lower phosphorus levels. So the document, it identifies the POTWs, public water treatment works in the basin, total phosphorus removal technology. We're going to talk about those just briefly. There's basically two that we're talking about. It's chemical addition or biological phosphorus removal. You know, I'm getting old enough, I can't read this small writing, so I'm almost ready to have to turn around here to read this. Optimizational strategies for both the chemical and biological processes, process diagnostics, case studies, training, resource funding, and technical assistance. So it's a very well put together document. I was really thoroughly impressed, and it really is focused on educational value. So when Majid, Phil, or I think about wastewater plants, it's not the way many of you who aren't directly involved in the industry think of them. We see a lot more than you probably see, like just a wastewater treatment plant. And while that's true, the same basic science-backed principles are true amongst most, or pretty much all, POTWs. There's nutrient assimilation. Anytime we're trying to grow biology, we need a carbon source, we need nitrogen, we need phosphorus, just like any of our bodies. What we're talking about here with phosphorus removal to meet permit limits is really additional phosphorus removal using chemicals or biology. This down here is a diagram, just one of the diagrams that shows the conditions, the sequence that have to be created in a treatment plant environment to facilitate biological phosphorus removal. It's actually enhanced biological phosphorus removal. So phosphorus in its basic forms, from a design, from an operational standpoint, there's basically three forms of phosphorus from how we look at it. Organic phosphates, polyphosphates, orthophosphates. Orthophosphates are real dear to us. First of all, it's measurable. To be measured in an aqueous solution, all other forms of phosphorus have to be digested, broken into, or oxidized to orthophosphorus. Orthophosphorus is readily precipitatable by metal salts, so we're talking ferric chloride, ferrous chloride, sodium aluminate, or alum, which is aluminum sulfate. And soluble phosphorus, PO4, is what its chemical description is the form of phosphorus that's released under biological conditions and then taken up like a sponge in subsequent aerobic conditions. So these are basically kind of how we think about it. But the main thing here, we're growing a biological system. This is what the Clean Water Act did for us. Secondary treatment, biological treatment. It's all about the sludge. The bacteria, the microbes, are all taking up these nutrients, phosphorus and nitrogen and carbon, into their cell mass. And there's assimilation here. So ratio of about 100 to 5 to 1 for every 100 parts carbon, we take out 5 parts nitrogen and part phosphorus. There is our uptake by assimilation. And I'm going to just touch on the next slide here. The additional phosphorus removal that needs to be done to meet permit limits. Generally speaking, chemical phosphorus removal works. It's by far the most common form of phosphorus removal. Relatively simple, chemical addition. You take soluble phosphorus, bind it to iron, aluminum, in these different metal salts I mentioned, and it drops out as a chemical sludge. So it generates an additional sludge in the treatment plant. And generally it's about the residuals of treatment that come out of these plants, the sludges, are generally about 1 to 2% phosphorus by dry weight. We talk about biological phosphorus removal. It's got some inherent advantages. It can really take the phosphorus concentration down quite a bit lower than chemical phosphorus removal can. It doesn't generate additional sludge, so there's not more material to deal with. But we can't make phosphorus just go away. We change its form. We try to concentrate it in the sludge. If you look here for biological phosphorus removal sludge, it's much higher in the concentration of phosphorus. So that's where it goes. The phosphorus is taken up into the microbes, into the cell mass. And it's about 5 to 7%. So good 3-4 times as rich in phosphorus as conventional non-biological sludge, non-biologically phosphorus removed sludge. So the big thing here, I said earlier, it's all about the sludge. You got to get the sludge out of the plant. If you don't get the sludge out of the plant, you're going to have problems. This is my last slide. Biology loves steady state. We should think about biology, process ideals. How would we do this in a perfect world to best suit the biology in the plant and get the most out of it? So another thing, anaerobic digesters, aerobic digesters, these other parts of treatment plants that process the solids and make them suitable for land application or disposal of one form or another. The side streams, we call them, that come off of these digesters to concentrate those sludges are very rich in nutrients. They should really be brought back at a time when the plant can best handle them. A lot of these simple ideas can really go a long ways to these treatment plants. Would you want to bring those high strength waste back in the middle of the day when our detention times are lowest and we got the highest loading? Or would you want to bring them back at night when our flows are low, there's more detention time, less food available for those microbes? And my final point, dual point metal salt feed for chemical precipitation. Most plants designed in the Clean Water Act era have dual point feed. A lot of them don't use it. But if you do use it, it can tighten the steering wheel of control at a treatment plant by dosing closer to the effluent end of the treatment system. And you can also reduce some of the loading to the bioreactor, the activated sludge system, to reduce the chance for excess phosphorus in effluent. I wanted to mention too, and I didn't, a lot of plants, solids inventory in the plants. It's so important. I was just at a plant yesterday that's really struggling with this over in the thumb. Unable to get sludge out of the plant. When you do that, you're exposing yourself, the plant is exposing itself to much higher chance of solids washouts into the receiving streams, which is inevitably going to blow your total phosphorus concentration. So just some of these simple, kind of reviewing the basics of treatment plant operations, very important. So I think that is all I have.